All right, ladies and gentlemen, this is going to go quick, but I do need your attention. Excellent. Okay, so enthalpy is what we call a state function, and that means it depends upon where you start and where you end, and it doesn't matter how you get there. So if you start at A and end at Z, as far as chemistry is concerned, it doesn't matter if you go from A to Z in 1 step or 26 steps, the difference will still be final minus initial. The final where you end minus the initial where you start is going to be the result of the change. Yeah. Okay. So Hess's law basically talks about that and explains that because enthalpy is a state function, it doesn't matter how you get to where you're going. Ultimately, your change in reaction enthalpy is always going to be products minus reactants. Final minus initial. Where you end minus where you start. So because of that, there's a really neat formula that makes it really easy to calculate reaction enthalpy. Wait, yes? Hess's law basically says what I just said. It doesn't matter how many steps you take, as long as you end at the same place, start at the same place, you'll have the same energy.
What minus what?
Products minus reactants.
Okay, so Hess's law products minus reactants.
Yep. And I'm going to show you the formula here in a little bit. But this basically also means that you combine reactions pretty easily. So consider the reaction A plus B yields D. You guys okay? We're good. Okay. A plus D yields, or A plus B equals D. Now, if A plus B plus 100 kilojoules makes C, and then C plus 50 kilojoules makes D, how many kilojoules do you need to add to A and B to make D? 150. It really is that simple. So you can combine reaction steps. Some of people like to diagram them, but they're ultimately products minus reactants. This is a fun little reaction diagram. This is more AP level. But can you see how the reactants are here and the products are down here? And the reactants here and the products down here? So obviously these are two different reactions because the humps are different sizes. But the starting point and the ending point are the same. So as far as thermodynamics are concerned, they're the same process. By the way, are these diagrams of an exothermic or an endothermic process?
Those are exo.
Exothermic. And we know it's exo because the products are lower in energy. So let's say the reactants are 100 and the products are 40. The reaction would be 40 minus 100 for a grand total of negative 60. Good.
Could you explain the Spider-Man meme?
The meme or how it applies to chemistry?
Yes.
Okay, so in the Spider-Verse, basically there's an infinite number of Spider-Men.
Yes.
And they can all encounter each other. Since there's an infinite number of them, there's an infinite likelihood that they will encounter each other in different realities.
Yes.
So they're like, hey, you're a Spider-Man, you're a Spider-Man. Well, in this case, there's 7 Spider-Men, but they're all Spider-Men because some are in 2 steps, 10 steps, 3 steps. 1 step, Hess's law says, as long as you start at the same place and end at the same place, it's the same process.
I get it.
Other questions? Moving right along. Okay, so this is how Hess's law is usually shown in its mathematical form. All of the products minus all of the reactants gives us our enthalpy of reaction. And if we already have the total number of reactants and products, then we can use a diagram like this to calculate the enthalpy of reactants. If you have a calculator, go ahead and calculate that. If you can do it in your head, do it in your head. If you can do it on paper, do it on paper. What is the enthalpy of reaction of that process? What is the enthalpy of reaction of that process in the diagram? It starts at negative 240 kilojoules and ends at negative 560 kilojoules.
Would it be negative 320?
Seth would like to know if it's negative 320. Question?
Wouldn't it be? Or not?
Sorry?
I have an answer.
Okay, what's the answer? Oh. Did you have the answer?
Yeah. Negative 800.
It's negative 320. Because, ladies and gentlemen, if you take a look at this. No, not that one. So let's look at. Do you guys need help? Can I help you somehow? Okay. So the reactants right here are at negative 240. And the products down here are at negative 560. So Hess would basically say that means that the overall reaction change from here to here is negative 560. That's our initial state, minus negative 240. That's our final state. So negative 560 minus negative 240, if math is still working the same, is 320, and the units is kilojoules.
That looks like exactly that.
Right. Does that make sense?
Yeah.
Yes.
What's the delta H RXN?
Reaction. So we abbreviate reaction RXN because I don't know why. I wasn't in the room when they decided.
Excuse me?
Yes.
And why is it reactants? Like, why is that?
Reactants and products.
No,
Products.
no. Why is it like bigger than the RE?
Oh, that's just a conversion. That's a conversion pickup.
Oh.
I used to do this in a program called Math Type, and then Math Type got discontinued, and Office tries to try to figure out what it's doing. So there's every now and then there's artifacts.
Wait, what's delta H?
Change. Yeah. So delta H is basically the change of the base. Okay. The deltas don't need to be there for the products and reactants. It really should be all the products minus all the reactants. Where you end minus where you start. Yeah, might as well.
Wait, products minus reactants.
Products minus reactants.
Equals delta of RZ.
Yep. So, in other words, what this is saying is the energy of reaction is equal to the energy of all the products minus all the reactants. It's this gap right here. Okay. If you're comfortable with this, give me a thumbs up. If any part of this is unclear, say.
Why isn't it just 320 if the change is 320? Why is it negative?
Because, okay, that's a good question. Seth asked, guys. Seth asked, why is it negative 320? It's because both of these numbers are negative. Remember how we talked about a bonded thing will have a negative energy? We're almost always going to be subtracting negative numbers. It's just because enthalpies are just negative because they're complex. Other questions? Off we go. All right. So, take a look at this. Oh, by the way, this is the way it's supposed to be written. It's supposed to have a sigma in front, meaning all of the. Okay, so keep in mind, guys. Okay, so keep in mind we're talking about all of the reactants and all of the products. Okay, here's probably the simplest chemical reaction. This is the combustion of methane. First of all, is this balanced?
Yes.
Yes. Good. So we got a carbon and a carbon, 4 hydrogens, 4 oxygens, 2 and 2 is 4 oxygens. So this chemical reaction is going to have a diagram that looks like this. Again, burning most things is exothermic. So here's our reactants, here's our products, and the difference between where we end and where we start is going to be our enthalpy of reaction. Okay. Now that's great. And if we're told what the total energy of each side is, easy, simple division. However, there's another way we can determine the enthalpy of reaction. And that is looking up the enthalpy values of each individual species. So you could look up the enthalpy values of methane, the enthalpy values of oxygen, actually. You don't need to look up the enthalpy value of oxygen because oxygen is an element. And all elements have what enthalpy? 0. Good. Do you remember why? Because they don't need to be made. Okay? They're already a thing. They don't need to be made. Okay, so we're going to calculate the heat of reaction when 1 mole of methane, CH4, is burned in excess oxygen, as much oxygen as we need, and then the enthalpy, the F is the formation enthalpy. Enthalpy of formation values of these things. There's methane. Oxygen is 0. There's water, and there's carbon dioxide. So, see if you can apply Hess's law right there and determine what the enthalpy of reaction is. I'll be a few minutes behind you. Go for it. You want the lights on or what?
No, it's fine. Yeah, it's not. Little buyers, and then take a picture of you and your dad at work today.
Where's the phone?
Yeah, but look,
Let's get it. Here you go. Sponsor.
ready? 1, 2, 3.
I'm just gonna set it up. I'm not gonna give you the answer.
Wait, you think he's a products minus reactive? Maybe he's reactive minus products.
Final minus initial. Wow. For some reason, the reactants got small.
So do you add the products or like?
Yep, you add all the products and you subtract them from all the reactants. Or subtract them by all the reactants. Okay, so what's one of our products? CO2 and
CO2 and H2O.
H2O. So those are our products. And what are my reactants?
Zero.
CH4 and O2.
O2. Okay, so we start by writing the chemical equation in, but we're not quite right because this does not balance the chemical. This does not match the balanced chemical equation.
No.
What's missing?
There's 2 H2s and 2 O2s.
2 H2s and 2 O2s. Now we just replace the chemicals with their book values. So CO2 appears to be negative 394. Water appears to be negative 242, but we're going to multiply that by 2. So plus 2 times 242. So those are all of our products. And then methane has the book value of negative 74.8. And oxygen is
0.
0.
Wait, Mr. Bush,
Yes.
how do we know what the book value is?
I'd give it to you. Yeah. Someone probably dead now looked it up, determined what it was. Okay, so go ahead and do that math. And hopefully it's going to be a very large negative number because most of the time when you burn methane, it releases fire. Negative 953 kilojoules per mole,
Is that right?
and it is per mole of CH4. Is it? I don't know. I just wrote that was good.
Negative 803.2.
Negative 803? We have some. Which one do you like better, 803 or 953? 803?
803.
803 kilojoules per mole.
I did.
Did you double the 242?
Yes.
I did negative 484 minus.
Why 484?
Where'd you
So there's 2 times 242.
Got it. Okay, so negative 484 plus negative 394.
Yeah, I got
Minus-
negative 878 and then minus 74.8. I got 952.
Minus negative 74.
Oh, add. Okay.
Really good.
Again, enthalpy values are negative because we're using compounds.
So that's 2 times 0.
Okay. Maybe.
Yeah.
I said it was that's 2.0.
2.0. Otis.
The thing on the, it's 2 times 0.
Yes.
And why is it 2 times 0?
Because there's 2 oxygens, and oxygen is an element, so elements have an enthalpy of 0.
And how do we know what's an enthalpy?
What the values are?
Yeah.
Like I said, someone probably dead now, put them in a book somewhere.
Wait, but we know it's 0 because let me see that one more time.
Okay.
Elements.
Elements are 0
Oh,
because you don't have to make them.
makes sense.
Remember when we basically have elements at the 0 level,
Yes.
and then when they bond, they become negative?
Yeah,
If something's just an element, it's at the 0 level.
that makes sense.
Other questions? Okay. And that's it for today. If there's no questions, you can go ahead and work on your work. And
Yeah,
yeah, I'm gonna fix that link.